In this section, we are going to discuss the partial derivatives. Partial derivatives are always more than one variable. When one variable, we say the derivative. The only function is y, function of x. X is an independent variable. X is changing with reference to that one. We are going to describe the change in the function. That's the rate of change with respect to x. But here the function is of two variables. For example, x and y are the independent variables, and both variables are changing. When both variables change, then it's very difficult to control the behavior of the function. So to control that one, we just use the idea that one variable is changing and one is fixed. We want to fix one of the variable in function of two variables. For example, we have function of x, y. Then we fix our x, only y is changing. We take the derivative, we study that one. And then secondly, we take y as a constant and x is changing only. So in this way, we can discuss the change with respect to x and then change with respect to y. If they are a function of three variables, then we say we take 2 as constant, 2 are not changing, 1 is changing. So we have three derivatives with respect to x, for example, with respect to y and with respect to z. So this is the idea we're going to discuss. Now, as we are going to fix, for example, two variables, we fix one variable and only one variable is changing. So all the formula we have discussed in case of the simple differentiation are being applied here in case of the second derivative. So I just described briefly the derivative with respect to one variable, and then we extend into variable more than one variable. For example, I have function y equal to f of x. So my basic definition of the derivative of the function at point x equal to a is limit h tends to 0 of the function here f of x plus h minus f of x over h. So this is the limit, and this gives me the limit of my derivative. I describe f dash of x, or I can describe this as df by dx. And we call this a rate of change of the function along the x-axis. Now, we have many formulas. For example, I have the function f of x is equal to x squared or x cubed. Now I can find the derivative of the function of this one. This is our power rule, and with the power rule we get here 3x squared. So it's n over n minus 1 we're having here. For example, I am having here the function, the value function is f of x, trigonometric function sine x. So derivative of this one is cosine x. So I have here the function as e to power x squared. So my derivative of the function is e to power x squared into derivative of d by dx of x. We call this as chain rule. Similarly, I can have here the derivative of cosine x squared minus 3. So my derivative will be minus sine x squared minus 3, and then I take derivative of the function x squared minus 3. I say this is my chain rule. For example, I have a very interesting example. I have the function e to power sine x cubed. So I want to find derivative of this one. Derivative of this one is e to power sine x cubed, and then we are having the derivative of sine x cubed. So again, we move and we can write this equal to e to power sine x cubed. Now the derivative is cosine x cubed, and then derivative of d by dx of x cubed, and so on. So there are some important derivatives. For example, I have 1 upon x. When I take derivative of 1 upon x, let's see here we can say this x to power minus 1, and derivative of this one is minus x to power minus 2. I will simply write here 1 upon x squared with the derivative of this function. So these are some of the important ideas in find the derivative. For example, I want to find the derivative of 1 upon root of x squared plus 5. So this will be, actually we can write here this equal to x squared plus 5 to power minus 1 by 2, or simply we can write this is minus 1 over 2 into root of x squared plus 5, and then we take derivative of x squared plus 5, that's equal to 2x. So these are the basic some formulas, applications in case of the derivative of one variable, because we are going to extend it to derivative of two variables. Now here I go to the definition, and we are having here the xy plane. This is my x-axis, and this is my y-axis. And these functions we can define more easily. This is my function y equal to f of x. So when I want to find derivative, this is my f dash of x. They're very simple one to define it. Now if I am having here the case of 3 dimensions, 2 dimensions, this is my z-axis, this is my y-axis, here is my x-axis, x-axis 0, y-axis and here is z-axis. So I'm having here I can say here I take some surface, and I want to find the derivative of this one along the y-axis. So I'm taking here this value. This is a plane. Here it's y0, and at this one we are going to get this as plane. This is my plane. I say this is curve, and this y0 here is the point y0. Now the curve is fixed. This is my curve along which I am going to discuss my derivative. So this is my curve, and along this curve I'm going to discuss my derivative. So this point here, I get here point x0, y0, and we having here also z0. So we are going to move along this curve, and along this curve when we're moving, we get the derivative of the function along the y-axis. So that we say f of y. So similarly, we can define along x-axis when we fix our x, and we discuss the function that one. So I have here the function fxy, and it's when moving along x-axis. This means the change is in x only, x plus h and y. If the function fxy is moving along y-axis, then my change is x, y plus k. So here, if I'm taking this point and then this point is along y-axis, and here x plus y plus k. Now when I want to find the change along x-axis, keeping y is not changing, so I say here's my limit, h tends to 0. I have here f of x plus h y, and then I have minus f of xy and over h. Now here y is not changing, only x is changing. So I say here I have the derivative. I describe my derivative as partial f by partial x. And then I am going to discuss the derivative, and I am going to have the derivative with respect to here. I say here f is changing along x, so it's the derivative along x-axis. It's the notation I will do. This my first definition. That's the derivative along x-axis. Now similarly, I can define my derivative along y-axis. I have here f of x, y plus k minus f of x, y over k. So this is my function and change in function, and here k tends to 0. This is along y-axis. So I say it's change along y-axis partial f by partial y and f of y. So here when we discuss the derivative, in this one we say df by dx, because they are a function of only one variable, so we take d. But here a function of two variables, so we don't take d, we say partial. So this must, you remember it, this is for the partial f over partial x. We take part of the derivative, we're not taking total one. So here we are going to, we have just mentioned it, this number 1 and this number 2, and we go to see some example how we can apply this one. It's very simple. So simply is like that you fix your y, you discuss the derivative with respect to x, then you fix your x and you take derivative with respect to y. The same formula we discussed in case of one dimensions, we are going to apply it here. You will find it in the example very interesting.